Hello everyone. Today I'm going to talk about why Ruby's JIT was slow. Let me introduce myself first. My name is Takashi Kokubun, and on the internet I use an IDE called Kokubun where the first O is actually 0. And I'm also working as a Ruby committer in my spare time. I originally became a Ruby committer as an ERB maintainer. I actually work on JIT compiler these days, and also some other features like IRB's coloring, release command, and show source command, which are going to be introduced in Ruby 3.1, and also other features like struct keyboard init that is going to be improved in Ruby 3.2. And I also work as a Treasure Data employee, and I work on storage services in our platform. Brief memory about my first Ruby Kagi is that it was in 2015 that we presented the high performance Hammer implementation, and these days we merged the newer version of the Hammer implementation to the Hammer core, and that's currently in the main branch. It hasn't been released yet, so I'm not sure if it's really going to be Hammer 6, but that's the current plan. All right, so the main part, why Ruby's JIT was slow. So in Ruby 3.0 release, we said that we achieved the Ruby 3x3, which is making Ruby 3 performance 3 times faster than Ruby 2.0. And we kind of achieved that in a benchmark called OptCarrot, which is an NUS emulator that is not the kind of real-world workloads like a web application. So we also said that it's not still ready for optimizing workloads like Rails. And I'm kind of sad that this happened because my main primary usage of Ruby is for Rails applications, and so I wanted to make Rails faster by just enabling the JIT compiler, but it actually didn't happen in Ruby 3.0 release. However, if you look at the benchmark of the JIT compiler with various versions, in the default configuration, as you can see, the JIT compiler's performance was slower than the virtual machine. Like in this graph, if the graph doesn't reach the 1.0, it means JIT compiler is slower than the virtual machine. On the other hand, if you change the configuration a little bit to use the max cache 10,000, that will actually go above 1.0 in the Ruby 3.0. That is actually 5% faster than the virtual machine. So we found that Ruby 3.0 introduced a good optimization that makes actually making it possible to optimize Rails by just enabling the JIT compiler if you are very careful about what configuration you use. So the default configuration of Ruby 3.0 was using only 100 methods at most for JIT compiler, but if you change the configuration to 10,000, that can actually make the Rails application faster. So we are going to make it the default in Ruby 3.1. So why was Ruby's JIT slow with the default configuration even with the default the 10,000 method that was slow in the prior versions? I think the idea is the MJIT architecture was making Rails slow, kind of, because MJIT uses C compiler and the DIL open to load the compiled code to the memory, and because each method is compiled as a shared library, and that is located in memory, not adjacent manner, that doesn't share some of the code used by the virtual machine. So if you compile, for example, say 100 methods, these 100 methods will not share many code, and like if that happens, that will make the iCache like a pressure iCache a lot. And the way we fix it in Ruby 3.0 is that by deduplicating, sharing the same code across different methods, finally we will not have any unnecessary or unnecessarily duplicated code in the memory. So the cache efficiency is improved in Ruby 3.0, and to fully leverage the efficiency, we need to compile everything to avoid thrashing the cache between virtual machine and JIT compiler. Other drawbacks of MJIT remains because even if we fix the cache problem, the compilation is still slow. Like when I benchmarked the Rails bench, I needed to wait for 5 minutes to just a single benchmark. So for example, if you want to optimize the Rails application performance by JIT compiler optimization, you need to wait for 5 minutes, and that makes the JIT compiler development very slower. And even if like it's not only for the JIT compiler development, but like if you use that in the production application, you will see 5 minutes will be used for warming up your application. And that is also a problem for the actual performance as well, because when GCC is running, that will pressure the CPU and also the memory usages, and then that will make Ruby main threads slower somehow. So if the GCC or like a MJIT is running, that will make the Ruby performance slower. So the comparison, because the comparison is slow, warm-up is slow, and also during the warm-up, the long warm-up, the actual performance is also slower, even if the purpose is to make the performance better by JIT compiler. And a trivial thing is if you use the PIC, which is position independent code for using data open as an architecture, you need to make the generated code a little bit slower for supporting that. And you can avoid that if you don't use syncompiler to generate the native code. So that's why JIT architecture matters for you, because if you, for example, requires to if it takes to warm up the application five minutes to warm up application, that makes your way to operate application different. Like if you want to servicing only instances that have the peak time performance, you need to wait for 5 minutes to compile the peak time methods and servicing that instances to the production. And also, because the compilation takes a lot of time, you may not be able to use that for usages that require a short amount of time for running JIT compiler and running the program. One example is that we were hoping to kind of introduce the MJIT for the competitive programming website called @Coder, but that was rejected because if you specify --JIT, it actually makes slower during the execution of the competitive programming that is allowed to use only 2 seconds. And MJIT has 2 problems with it. One is it takes time to stop the MJIT thread, so it needs to wait for the current compilation, which is sometimes taking hundreds of milliseconds. And the other problem is, as I said, during the compilation, that makes the Ruby main method slower. And I think there's another problem to take care of, which is to disable kind of default Ruby gems, because if you just use the main prelude, that takes a lot of time to compile everything. And so I think 2 seconds is not enough to compile everything of the prelude. So you need to disable gems to make such things not happen. Another thing is other people developing CDB JIT compiler called Vladimir is saying successful optimization of JIT compiler for CDB could prevent Go language eating Ruby market share. So like if the Ruby's JIT compiler is fast enough, he's saying we could make Ruby popular in the area we are currently doing, and Go language is improving in the market share. Another person working on YJIT is saying dynamic language without good JITs are going to extinct, and what she means here is Python is going to extinct because it currently doesn't have the good JIT compiler. So if you want to prevent Python from taking over Ruby's market share, like web application areas, we need to make Ruby's JIT compiler good enough to outperform Python, for example. So JIT architecture impacts the performance. So that's important for making these kind of things happen. So the goal of this talk is to discuss the JIT architecture of Ruby so that we can achieve those, like do not prevent those kind of unwanted things from happening. And also JIT authors could share some of the effort to develop the JIT compiler, because currently, as you can see, multiple people are working on JIT compiler of the CRuby, and some of these are kind of duplicate work, although in some other cases we share the work to MJIT and YJIT are sharing some techniques to bring the same kind of optimization to both of the implementations. But to make it happen, we need to kind of share the architecture between these other different implementations. And sorry, my picture is not needed here. So to summarize what's going on right now, Shopify is currently developing another JIT compiler implementation called YJIT, and Vladimir, that is shown as a human picture here, is developing JIT compiler infrastructure called MIR, and that is, I think sometimes it's confused, like Mir is a compiler, JIT compiler, but also we could use that at the same time as the current MJIT compiler, because MJIT compiler currently generates C code, and Mir could take C code as an input for generating the Mir interpreter representation. So we are hoping that could also be an internal step towards the ideal performance. But at the same time, we could also directly generate Mir interpretation so that compilation time will not be worse than the ideal performance. And that's the Vladimir was saying for the future plans. And formerly, Vladimir was working on replacing the current virtual machine called YARB to RTL, but that plan was kind of abandoned because we were able to achieve the same kind of performance without changing or replacing the entire virtual machine. I will talk about that later too. Oh, sorry. So what I'm going to discuss is these. So first of all, maintainability matters, and also internal representation is important for optimizing the JIT compiler, or like making it possible to maintain and also achieve the ideal performance, or also for portability, and how to compile generated code, and what optimization is feasible for each architecture. So the first part is maintainability. The reason why we chose MJIT as a first implementation or like an architecture for JIT compiler of CRuby is because it's very good for maintenance. So if you use MJIT, you can generate code in C code, and C compiler can generate the debug information for C code, and so you can go through what code is executed by GDB very easily. Whereas if you use YJIT or Mir without using C code, you need to see the native code to debug the generated code, which I think is possible, but at least it's harder than just seeing C code. At least I think C code is more readable than native code. And another thing, or like another benefit of using MJIT was we could support new instructions of the virtual machine automatically, which means like, so virtual machine of CRuby is implemented in C. So if you generate the native code by C compiler, you can reuse the virtual machine's implementation as is, and just for example, like if the virtual machine instruction called opt class is implemented in or like added to virtual machine, you can just copy paste the opt class to the native code, and so you don't need to manually implement the JIT compiler for that particular instruction, even if the virtual machine maintainer was only interested in maintaining the virtual machine. So even if I don't do anything, JIT compiler is automatically maintained because we have this capability. However, we still generate the optimize code by manual optimizations for particular instructions we care about. For example, sender instruction, which is for method dispatch, and instance variable get instruction, which is for instance variables. So these two kind of things are optimized well in MJIT, and for those things, we override the current implementation to more optimized implementation so that we can leverage the runtime information to optimize these instructions. And some people think MJIT just copy paste C code to like the original C code to the function and just lets GCC do everything, but it's actually not true. Like if you just do that, the optimization possible in there is very limited, and if you need to leverage the runtime information of Ruby virtual machine and let GCC know that you need to hard code those kinds of things manually in the MJIT compiler. So that's what the current MJIT compiler is doing, and even if we stop using MJIT, that will be still feasible. Like the idea itself is it will be useful for other implementations like YJIT or mirror-based compiler as well. Another discussion point is we could possibly rewrite the C JIT compiler implementation currently in C to Ruby because as you can see, Ruby is much more readable, and that's why you were using Ruby, I guess. And so, for example, in Truffle Ruby, the GraalJIT implementation is written in Java, whereas the original C2 JIT compiler was written in C++. Java is a target language for JVM, so that's easier to maintain for those people. And because we maintain Ruby interpreter, writing the JIT compiler in Ruby could be easier. However, this actually gives some problems for performance and maintainability as well. Because if you use Ruby as a JIT compiler implementation language, you need to take care of the JIT compiler implementation itself in the JIT compiler as well. And I've kind of had some ideas to improve that, but we need to figure out how to deal with these problems, like creating the Ractor and stopping it every time so that will be not impacting the main threads afterwards, or create a process and talk to that process to just use the Ruby as a compiler process, and that will not impact the main process. The next topic is internal representation. To optimize the JIT compiler well, we need to have the internal representation to deal with the information that is not in virtual machine. So there was a project called RTL that was all of the instructions were rewritten in the virtual machine, and we didn't introduce that feature because we believed that we don't need to do that for optimizing the JIT compiler, and we kind of overcome the performance of the RTL MJIT by the Ruby 3 JIT, and so we proved that we don't need virtual machine replacement. However, the RTL had a kind of good ideas, so RTL had two ideas. One is register-based instruction, as the name says, and also the other is speculative instructions. What speculative instructions do is to it works like a provider of runtime information. If you run the plus operation, that will be converted to, for example, int plus, so that will be specialized to integer-based instructions. And by doing so, virtual machine can profile the runtime information and let JIT compiler do the optimization for integer-specific code. And alternatively, we could do that without using changing the virtual machine instructions, and that's what Ruby 3 is currently doing. So the current MJIT generates the most speculative code first, and then if the speculative assumption is failed, we recompile the code with disabling the speculation for that optimization. And YJIT, I think, is doing a similar thing. It internally maintains the information for each basic block, and basic block versioning maintains that, for example, a type information for each basic block, and so runtime information is baked in the basic block information, and YJIT can leverage that to optimize code further. Another thing we need to care about is C method inlining. So as you know, C Ruby is currently implemented in C in many places, and many methods are written in C. So to inline methods like written in C, you need to use infrastructure that can be converted to convert C to internal representation like LLVM or Mir. And we could also change the C methods to Ruby, like just rewrite the core implementation in Ruby. And that is, both of these are helpful for optimizing the performance of the JIT compiler, but we could also do both. Like Giraffe4Ruby is taking both approaches, I think. Like C extension can be converted to their own IR by LLVM, but many other methods are written in Ruby, and so Ruby-specific optimization are possible there. Another layer is compilation and code generation. So MJIT is concurrently compiling the methods in a MJIT worker thread, but YJIT is synchronously compiling the methods to native code in the main thread. That's not a problem if the JIT compilation is fast enough, but MJIT is obviously very slow about the JIT compilation, like taking hundreds of milliseconds. So we cannot do that synchronously in MJIT, but if you change the architecture like YJIT and Mir, and where the compilation is faster, you could synchronously compile that, and it's very easier to like develop because you don't want to spend 5 minutes to every single JIT compiler optimization, and also warm-up is very slower if you use MJIT. And there are other options for generating a native code. Like we currently use C compiler to leverage the maintainability and also like debugging, but it's as formerly like before Vladimir said, the MJIT is startup time is or like compilation is slow because GCC and or like Clang spends a lot of time on warming up or like initializing the compiler itself. So if you can initialize the C compiler infrastructure only once and reuse the same thing a lot of time, the compilation will be faster. But problem is if you, for example, use LLVM to initialize it only once and use the same infrastructure again and again, that will be still having troubles like binary size of the CRuby interpreter, because LLVM binary size is very large. So if you ship CRuby with LLVM, that will be making the implementation very larger. And you could, if you use Mir or like a YJIT, the implementation is much smaller than LLVM, so that will be having no problem with that. Also, if you think about the architecture, you need to care about what optimization is feasible. So currently, MJIT is just using call instruction to dispatch the native code, but we could use direct threading like a virtual machine to leverage the like YJIT is doing the technique to making the dispatch more granular, but they also ended up using call instruction, and they said it's actually faster, so it's actually not a problem for MJIT either. Another thing is the optimization. So on-stack replacement is to optimize the current methods on stack to more slower version so that we will discard the speculative code. But MJIT is using C compiler, so some of the very low-level information is not available for this, so it's not possible for MJIT. Method frame skip is a technique we are building in recent versions. That's to skip frame push of Ruby backtrace. So if you know what C method or like a native code you're using in the backtrace, you can skip the frame and lazy push that when the method raises something or like when the frame is actually needed. So that requires the native information, but we thought that it's also possible in MJIT as well, so we are going to implement that. In conclusion, JIT architecture may impact various things listed here, so it's not just for JIT developers' problem. We also need to think about what will be caused by the architecture we choose. That's it. Thank you for listening to my talk.